My name is Jialei. I'm a PhD student from University College London. Welcome to our presentation on screw theory-based stiffness analysis for a fluidic-driven soft robotic manipulator. This is a collaborative work between King's College London, University of Santa Catarina, and University College London. The material used in soft robots are usually with Young's moduli less than 1 G-Pascal. However, in rigid link robot, that value is usually larger than 10 G-Pascal. As such, in rigid link robot, the stiffness can be adjusted via variable stiffness joints, but with the decrease of Young's moduli, variable stiffness links or continuum robot come into reality to further change the stiffness of soft robot. The compliance of continuum robot dramatically increases compared with rigid link robot and distributes evenly. Because of the high compliance, the mean body of soft robot usually undergoes relatively higher deformation. The physical joints also don't exist in soft continuum robot. All these changes make the stiffness analysis of a soft robot still a challenge. For the introduced softness, how to quantitatively assess and improve it, how to identify the stiffness capability of soft robot is of paramount importance, not only for robot design and modeling, but for practical application. For instance, a soft gripper should have sufficient stiffness to pick up stuff, and in medical application, the robot should have different stiffness response in different areas. In current research, different kinematics modeling methods have been proposed in soft robot field, which normally can be divided into activation space, arc configuration space, and task space. In opposite direction, it is the inverse kinematics. Because there is no physical activation joints, the Jacobi-based stiffness transformation is impossible. The stiffness analysis usually is based on finite element or experiments. However, how to bridge the kinematics and stiffness together and analyze the configuration-based stiffness still remains to be further explored. The contribution of our work could be summarized into two aspects. Firstly, based on a pneumatic-driven soft continuum robot, we propose a method to analyze the configuration-based stiffness and the stiffness in specific direction. Secondly, the connection between kinematics and stiffness is established based on screw theory, which makes the proposed method have the potential to be applied into different kinematics. The manipulator used in this paper is a pneumatic-driven soft robot for minimally invasive surgery. The main body is made of silicon. The chamber is surrounded by a thread which restricts the radical expansion but allows the longitudinal elongation. There are 6 embedded chambers in the robot. When all the chambers are pressurized simultaneously, the robot will elongate. While some of the chambers are pressurized, the robot will bend. The forward kinematics in this paper is based on the piecewise constant curvature assumption. The arc is described using 5 twists with different screw axes and amplitudes as shown in this table. The screw parameters are calculated by the range resulting from pressurization. By exponential production, the transformation matrix is derived from the twist. As long as the forward kinematics have been derived, the relationship between element compliance and the global total compliance could be established. As shown in the left side figure, the element compliance can be transformed from body frame to global frame by predefined adjoint matrix. The continuum robot is regarded as the combination of finite serial connected elements. Then the total compliance equals to the sum of all the element compliance written in global or body frame. Once the general 6x6 stiffness matrix is obtained, then the deflection model can be used for further stiffness analysis. In order to take the change of system parameter due to elongation into consideration, additional pressure-dependent parameter compensation is adopted to calculate the screw. In summary, the output of the proposed method contains both kinematics and stiffness. This is convenient for conducting the configuration-based stiffness analysis. In addition, the output stiffness is not only located at the tip position, but along the manipulator. This reveals how the stiffness evolves at different positions of the robot. There are two sets of experiments: forward kinematics validation and stiffness validation. In kinematics validation, an AI-DAC device is used to collect real-time pressure information and generate the PWM signals to control 3 individual pressure regulators. Position in 3 directions is recorded by an AI Aurora electromagnetic tracker. A 6 degrees of freedom magnetic sensor was mounted at the tip of the robot. 3 chamber pairs are pressurized with 0.4, 0.8, and 1.2 bar in turn. The pressure increases gradually to simulate the quasi-static process. The result shows that when the pressure is less than 0.8 bar, the maximum error in 3 directions is below than 5 mm. The error increases when pressure equals to 1.2 bar. The choice of compensation parameter mainly influences the accuracy of the forward kinematics. In stiffness validation experiments, a 6 degrees of freedom force torque sensor was attached to a motorized linear rail to measure the directional stiffness. The control part is the same as forward kinematics part. The displacement and force could be recorded, so the experimental stiffness is obtained. Based on the stiffness matrix and the deflection model, the simulated direction stiffness could be calculated as well. The result shows the stiffness in x-axis increases from 0.2 Newton per centimeter to 0.6 Newton per centimeter, about 2 times variation with the bending angle increases. The stiffness in y-axis gradually decreases, but in this prototype, the variation is small and almost constant. In that axis, the stiffness decreases with longest variation, starting from 11.1 Newton per centimeter to 0.2 Newton per centimeter. The stiffness prediction along the robot and the different configuration is given. It is found the overall stiffness decreases with the increase of the pressure. However, in specific direction, the stiffness may increase. The stiffness also decreases along the manipulator, but in different directions, it has different response. This prediction reveals the underlying stiffness property of the robot. Such result could be used to determine which direction of configuration would have high stiffness in order to achieve on-demand stiffness analysis and improve the stiffness capability of soft robot. In summary, a square theory-based methodology is proposed in this paper, which incorporates the forward kinematics and the stiffness modeling. The method can also be used to achieve a configuration-based stiffness analysis and reveal the stiffness evolution along the manipulator. As for the future work, we will take the hyperelasticity into consideration and improve the accuracy of the proposed method. We will also implement proposed method into different forward kinematics. Thanks for listening.